Hi, my name is Kevin Chen, and this is Lab 3 Circuits for Physics 2212 at Georgia Tech. So the purpose of the lab is to apply principles of energy conservation and current conservation to predict the behavior of circuits containing resistors in series and parallel. To examine the behavior of ohmic resistors and capacitors, use multimeters to measure the actual values of conventional current and potential differences in the circuits. And for our results, we calculated the resistance of a 47 ohm resistor to be 48 ohms. A resistor of 100 ohms was calculated to be 102 ohms. The wire and ammeter were found to have 0 ohms of resistance. And it took 6.02 seconds to charge and 7.1 seconds to discharge a resistor that had 10 ohms, and it took 11.3 seconds to charge and 12.1 seconds to discharge a resistor at 20 ohms. And using plotted data, we found the RC time constant to be 5.88 seconds. Going into the fundamental principles, we have the node rule, which is the current flowing into a node must be equal to the current flowing out of the node, and this is the result of the conservation of charge. We have the loop rule, which is the sum of all electric potential differences around a loop is zero, and this is a result of the conservation of energy. And we have Ohm's law, which is a current through a conductor between 2 points is proportional to the voltage across the points, and this is calculated by V equals IR, where V is the voltage, I is the current, and R is the resistance. Going to the charge of conservation of energy in series circuits, we have to first consider this diagram below, which consists of a circuit with 2 batteries, 2 resistors, and 2 ammeters. And we're told to predict the currents of I1 and I2, which should be measured by the 2 ammeters. And the initial conditions are the battery produces 3 volts, the resistors have 147 total resistance, or 147 ohms, and by using Ohm's law, we find that the current is 0.0204 amperes. By simulating the circuit online, we can see that the current from the ammeters match what we calculated. When we reverse one of the connections to one of the ammeters, nothing changes and the value stays the same. When we replace one of the ammeters with the voltmeter reads negative 3 volts while the ammeter reads 0 amps. The ammeter reads 0 amps because the voltmeter has high resistance, making the circuit function like an open one. The voltmeter reads negative 3 volts because there are no other voltage drops. Voltage from the battery goes directly to the voltmeter. I closed the circuit with a wire and used the voltmeter to measure the potential differences for parts of the path around the circuit by touching the 2 leads of the voltmeter to the different points that I needed to measure. The current was 0.02 amperes, and according to the loop rule, the sum of all individual potential differences for a round trip around the circuit should be 0. And as you can see from adding the measured potential differences in the simulation, they sum to 0. Here we have a graph for electric potential versus position around the circuit. It shows the increase and decrease in voltage as you go around the circuit, and batteries contribute to voltage gain while resistors contribute to voltage drop, and at higher resistance there is a greater drop in voltage, and as you can see the sum of all voltages lead to 0. When we attach a voltmeter to the circuit, why doesn't the ammeter reading change? So the ammeter reading does not change because the voltmeter has a very high resistance, so almost no current flows through it, and there's essentially no effect on the path and speed of the electrons. When I connect the voltmeter across the 100 ohm resistor, the voltage is negative 2.04 volts and the current is 0.02 amperes. When we replace the voltmeter with an ammeter in parallel with the 100 ohm resistor, the current through the other ammeter is 0.06 amperes. The ammeters have low resistance, so the electrons will flow through them instead of the 100 ohm resistor, and the overall resistance of the circuit is lowered from 147 ohms to 47 ohms. To calculate the resistance of each of the circuit elements, I used Ohm's law to find that this resistance is equal to voltage divided by current, and plugged in the electric potential measurements. For the 47 ohm resistor, the resistance was 48 ohms. For the 100 ohm resistor, the resistance was 102 ohms, and although they are close, the numbers are slightly off due to rounding, and the wire and the ammeter do not have resistors, so there is 0 resistance. Moving into RC circuits, which are the resistor capacitor circuits, we have one that is shown charging and one that is shown discharging. We have a 9-volt battery and a 10 ohm bulb, 20 ohm bulb, and a 0.2 farad capacitor. When I connected the batteries to the 10 ohm bulb and capacitor in series, the bulb lit up and then slowly faded. When I disconnected the battery and connected the capacitor directly to the bulb lit up and then faded out. When I first connected the battery to the capacitor and 10 ohm bulb and the capacitor was charging, the current began to decrease over time. When I removed the battery from the circuit and the capacitor began discharging, the current decreased over time. When I timed how long it took to charge the capacitor, for a 10 ohm bulb it took around 6.02 seconds to charge and 7.1 seconds to discharge. For a 20 ohm bulb it took 11.3 seconds to charge and 12.1 seconds to discharge. I set up a circuit with a 9-volt battery, a 0.2 farad capacitor, and a 30 ohm bulb. I measured the voltage across the discharging capacitor with a voltmeter and plotted 20 seconds worth of voltage versus time data on a natural log of the current voltage over initial voltage over time versus time. I set up a circuit with a 9-volt battery, a 0.2 farad capacitor, and a 30 ohm bulb. I measured the voltage across the discharging capacitor with a voltmeter and plotted 20 seconds worth of voltage versus time data on a natural log of the current voltage over initial voltage versus time. The predicted time constant was found by multiplying the resistor and capacitor values. And from the data, we got our time constant by dividing the -1 by the slope, which was negative 0.170, which was calculated to be 5.88, and this was close to the predicted time constant for the RC of 6 seconds, and the difference may be attributed to errors with using the stopwatch. Going to assumptions and experimental errors, there may have been human error in stopping the watch and capacitor from discharging at the same time. Online simulated models may also not be accurate to real-world circuits since there are many factors that are not accounted for, and the online models assume components and power source function perfectly. So moving into the discussion and conclusions, what if we used a real ammeter? Real ammeters have a small amount of resistance, which would reduce the total current, and when connected to the circuit, it would have slightly increased the total resistance and therefore decreased the total current. So what if we used an actual battery and no resistor? Our ideal model would predict that the capacitor is charged instantly, which would not happen in real life because there is some internal resistance in actual batteries. This brings us to the end of Lab Report 3 on circuits. Thank you for watching.